My name is Toon Koenen and I'm application specialist at Delmic for the Spark cathode-luminescence system, and I will tell you a bit about time-resolved cathode-luminescence. Time-resolved cathode-luminescence is a technique in which you look at the time dynamics of the cathode-luminescence emission process. In particular, you look at how fast light is emitted from a material when it is irradiated with electrons. Besides that, you can also look at how the light is distributed in time, and in particular how photons, which are individual light quanta, are separated in time. There are more or less two techniques which are used for time-resolved cathode-luminescence. First one, you look at what is called the lifetime or the decay, emission decay of the cathode-luminescence. Typically in that case the sample is excited by a short pulse of electrons, after which you look at how the light decays. And this emission process is stochastic, and so you repeat the experiment a lot of times, and in that way you build up a histogram of how the sample decays. This is an example of what such a typical decay trace looks like. And so on the vertical axis you have intensity, and on the horizontal axis you have the time delay. And so at zero is when the sample is excited, and after that you see a decay, which is typically exponential. This exponential decay is captured normally by the what is called the lifetime, which is the time delay at which the initial intensity has decayed to 1/e times the initial value. And this is a key quantity in optics and material science. Lifetime looks at how the light emission process occurs after it is excited. Another approach you can take is to see how the light is distributed in time. For that you can look at the G2 function, or the second order correlation function as it is known in physics. And this is essentially describes the probability of seeing more than one photon at the same time, or the probability of seeing photons at the same time. There are multiple cases in which you have interesting G2 behavior. And this is a first example where the probability of measuring two photons simultaneously is 0, indicated by this dip here. And this type of behavior is indicative of a single photon emitter, as is used in quantum optics. And this behavior is called anti-bunching, and so it's very important for people that work in quantum optics. In cathode luminescence, it's also often encountered that you see bunching, where you have a high probability that you encounter multiple photons at the same time. And this happens because the electron has a lot of initial energy that can excite multiple photons simultaneously, leading to this rich bunching behavior. And this also has a number of interesting applications within cathode luminescence. Experimentally, the two techniques, lifetime imaging and G2 imaging, can be done as follows. And let's start with the decay trace acquisition. For that, as mentioned, you need a pulsed electron microscope, which can either be pulsed by means of an ultrafast laser system or by using a static electrostatic blanker. For the rest, what you need is a fast detector, such as an avalanche photodiode or a photomultiplier, which is connected to a time correlator system, which records the time at which the photon is detected with respect to a triggering signal, which is also used to trigger the electron microscope. By doing that, you can reconstruct this decay curve. For the G2 acquisition, you use a similar approach, where you, rather than having one single photon detector, you have two, and in between there's a beam splitter. And this is called a Hambry, Brown and Twiss interferometer. And this allows you to measure this G2 function and the probability that you detect two photons simultaneously. One nice thing is that the G2 acquisition you can also do with a continuous beam electron microscope, although it's also possible to use a pulsed electron microscope, which has certain advantages for the signal to noise ratio. I briefly want to explain something also about the use of time-resolved cathodoluminescence for various fields of research. The lifetime can be used as a fingerprint to, besides color and intensity, what is normally already used to fingerprint materials, the lifetime provides another handle to identify particular defects or particular materials. Next to that, the lifetime is also very strongly linked to material quality, such it can be used to characterize materials and to improve the performance of the materials. Also, and this is maybe a more fundamental link, but the lifetime is also very much linked to the optical environment and to the local density of optical states. And that's a key quantity in optics that defines how strongly light interacts with matter and vice versa. And the lifetime can nicely gauge that, and so this has a very powerful method to dive into those types of effects and, for example, see how material behaves in the vicinity of a cavity or an antenna. The G2 analysis can, for example, be used to look at quantum emitters to see how they behave. And from the G2 analysis, you can also get an idea of the lifetime of the emitter, even in a continuous electron beam. To summarize, these techniques can be used in materials science, in photonics, and maybe even in geology and biology. And so it's a very broad technique and very general. The Spark can be used to accommodate all of these time-resolved acquisition techniques. One great benefit of the Spark system is that these time-resolved acquisition methods are nicely integrated into the software and into the hardware. And so this allows you to easily acquire this type of data. And for example, also to synchronize these acquisitions with the electron beam scanning. You can do a lifetime mapping or G2 mapping with a very high spatial resolution, and that goes beyond what you can do with an optical microscope, for example. This makes it a very powerful system.